Hello and welcome to our next discussion. So if you remember what we talked about in correlation, our very first example, where we compared loneliness and depression, we talked about correlation. And now a follow-up to that is when we look at these data points and we look at a correlation, suspected correlation, whether it's significant or not, that's something we do need to check in this process. But let's just look at this. There definitely seems to be a correlation between these sample values. But what is that, and how do we describe that relationship that we see here? Some line. Let me make it a little bit more straight liney that I want to describe. And that is called regression. When I'm trying to find that line, that equation that describes these two and their relationship. Not sure which one causes which one, if there's something else that's causing both, that's not the issue. If I have a loneliness score of 5, let's say, what, according to this line, is a good prediction for the corresponding depression score based on this? That is the goal. So if I take, let's say, SAT scores and college GPA, I can call one the predictor variable given the SAT score. What is the prediction of the college GPA? The predictor variable, sort of mathematically in my mind, is the input variable, and the criterion variable, the one I'm trying to predict, is my output variable x to y. So I'm going this way in my mind. However, if I just look at what notation we're going to look at first before my however, we're going to use a little hat there to indicate that this is a prediction and it's not necessarily the corresponding y score that I get. I'm going to have a linear equation to describe that relationship. If you remember linear, maybe you remember it as y equals mx plus b. It's the same, but for some reason the b is now the coefficient of x and the a is the constant term. Just in case you see it in a more statistics oriented book, it might look more like this. So we have a possible example, many examples, but one possible example for the a and the b value is a could be 0.3, b could be 0.004, and then I have my formula over there to use to predict a college GPA given the SAT score. So if a student's SAT score is 700, I plug that in, I get a predicted GPA of 3.1. Of course, that may or may not happen, right? Exactly like that. There is still variation here. SAT score of 200, plug it in, I get a predicted GPA, and so on. So I have my formula, which corresponds to some straight line that attempts to describe how I can use one variable to predict the other variable. However, there are many lines. If I look at, for example, two different variables here, hours slept last night and how that is related to your mood rating. I have these data points over here, and there are many lines, many rules to, I don't want to use the word rule always, many formulas, many equations to describe the connection that I can use to predict, well, if I slept 9 hours, Do I use rule 2 to predict 4 hours of, a 4 mood rating? Or do I use this line to predict 5.5? Or this line to predict a 6? Or this line to predict a 6.5? Which one is the best? Undo all these dotted lines. The most appropriate, the best line formula to use. They all follow this formula for a straight line equation, but with different A's and B's. Which one is the best? Well, what does best mean? I guess my quotation should be there. What does best mean? So what we're going to mean by the best line, if I look at this, is we're going to measure these errors. Let's suppose we have a line. Take any line you want. Then you can measure the difference between the observed value and the predicted value. That was supposed to be a curly bracket. Now, maybe there's going to be a point that sits right on it, but most of the time it's going to have a little gap between it, right? All these errors. Some of them are going to be a positive error between the observed score and the prediction. Some of them are going to be a negative error. Positive here, negative. It's trying to find that middle ground. How do I find that middle ground? Well, I'm going to try and minimize all these errors. But because I have a positive and negative, I don't want the errors to cancel and then make it seem as if there's nothing. So we're going to call the best line the one that minimizes the squared errors. Now, we don't have to worry too much about why squaring and all the detail. Essentially, the squaring makes sure that positive and negative cancellations don't happen. We also call this the least squares fit, because it's the smallest sum of the squares between the data points and the predicted values on the line. So that is what we mean by best. Let's go. So there are many here. It could be that rule 4 turns out to be the best here, but we're going to have to calculate that. Now, of course, that is a little bit messy to derive where those formulas come from. When I minimize the square of the errors, it turns out that these formulas do exactly that. So now remember, you have your general formula, the coefficient of b, which is also called the slope. And here, this one is called the intercept, if I can write properly. Intercept. Now the slope is much more important, but I have what we call here in pre-calculus slope-intercept form of a linear function or equation. So we need to calculate the b and the a. We calculate the b first this way. We call that the regression coefficient. So again, I have my x and my y scores, and I look at the deviation from their corresponding means, add them up, divide by the sum of the squares of the x's. I'm not going to read through all of this. You can pause and read through. It's just stepwise guiding you through this. But it's very similar to the correlation calculation in a way. And then the a, the intercept, the constant term, regression constant, they call it, is then calculated in a much simpler calculation. The mean of the y scores minus the b that I just got, times the mean of the X scores. So the only tricky one here is the regression coefficient. So let's look at an example where we do that. So let's go back to the number of hours slept versus happy mood. I may have done my correlation investigation. Perhaps I found that there is a positive correlation, which we see the diagram here. These are my data points. I suspect positive correlation. I've done all that. The correlation coefficient I found, if you wanted to do it yourself, it's also in the book, is 0.85. And now I'm ready to calculate using those formulas. So I calculate for X, the deviation scores, and then squared deviations for the sum of the squares, which feature in my formula here, sum of the squares of the X scores. And then the deviation of the Y scores, and I multiply those two deviations, sort of cross product there. And then I plug that into my formula to get a B of 1. Then I calculate A with the formula shown here. Much simpler to get the corresponding value of A, and in this case it's -3. So the best line is -3 plus 1 times X. Let's write that over here. Best line, predictor line, is -3 plus 1 times X. And I can use that for a variety of things. Let's write over here and say, let's say make a prediction here. If I sleep 9 hours, my predicted mood, according to that scale, of course, predicted mood score is -3 plus 1 times 9, which will be 6. Now I don't have the line here. 6 will be over here, so I'm suspecting that the true least squares fit sits somewhere over here, but I don't want to show that. It's too many lines on one spot, on one graph. But we can use that regression line, least squares fit, best fit, prediction line, called whatever you want, to make a prediction. If I have a value of one variable, I can make a prediction for the other corresponding variable. The 0.85 here, we can briefly talk about that, the correlation coefficient. How I can interpret that, I can square that as we did in the previous video on correlation. Let's just see what we get when we square that. 0.85 squared, so times itself, is 0.7225. Turn that into a percentage, 72.25%. That is the proportion of variance or variability accounted for by the other variable. So 72.25% based on this, so it's approximately, of the variance in mood rating, let's just say it briefly comes from hours, let's capitalize that guy, hours slept. Now my H looks super weird. There we go. So of course, other things affect your mood, but based on this still a very small sample, roughly 72.25% of your mood rating is somehow directly or indirectly coming from hours slept. And that is very useful information. Again, we're not saying hours slept causes your mood. Could be by way of other variables. There is almost 30% other factors affecting your mood somehow. But this kind of interpretation is certainly very nice and simple for people to understand. So it's definitely something that I want to be able to do. Okay, so that using those formulas, we have an example here, as well as how to interpret that. One more thing I wanted to do here is the regression coefficient B. Here's 1. How do I interpret that? So I check once. I don't want to write behind my webcam here. What I usually do is I make that fraction, so it's 1 over 1. So the top one is going to indicate the change in my y variable, and the bottom one, the corresponding change in my x variable. If you remember pre-calculus, rise over run, change in x over change in y. And then I'll say, I have space here to say stuff. Let's say it down there. Now, remember which one is which, right? The bottom one, x, is your hours slept. The top one, y, is your mood rating. So if hours slept, I say the right thing, I don't write the right thing, increases by 1, this 1, I always write it bottom up. So I look at the change in the x variable and then the corresponding change in the y variable. Now in this case, they're both 1. We'll mix it up in a second. Then the mood rating increases by 1 as well. Of course, that could be different. Let's look at some examples here. Let's suppose we didn't get a B equal to 1. Let's suppose we got a B equal to 2. I'm going to then write that as 2 over 1 and say if hours slept increases by 1, remember that's the bottom, then mood rating, according to this, increases by 2, if that was my B. I could have a different B. Let's say I have a B equal to negative 0.5, just as an example, so we can run through the possibilities. The simplest way I would do it is to just put that over 1. It's not the only way. I'm going to say something in a second. It is a way that will always work. And then I can say if the hour, I start always from the bottom. Hours slept is the bottom variable x, increases by 1. Then the top is the mood rating. Mood rating, now it's a minus, so that means decreases by 0.5. So if I increase my hours slept, according to this, my mood goes down by a half. I could also write this as negative 1 over 2 because it's a half. And then I could say, I'm just going to say it briefly here, hours slept increases by 2, I'm always going to put the negative with the top one to make the interpretation easy. Then mood decreases by 1. So lots of different ways, but they're all essentially the same, slightly different words, different numbers to interpret this regression coefficient, but very important that you are able to do that. Okay. So lastly, I want to just note that the presence of outliers drastically can affect my correlation results and my regression results as well. They're very much affected, they're very much connected to each other, right? Regression is really a continuation of correlation. I establish a correlation. I then want to describe that correlation, and that's regression. So if I didn't look at this guy, then my correlation is quite strong, positive. I just sort of pretend that's my least square fit roughly. My regression line, I can make predictions, probably going to be significant. It looks pretty good. However, with the existence of an outlier, it really pulls and shifts the correlation coefficient. And now suddenly the correlation is negative 0.11, which doesn't really agree with everything else. It's just that extreme score pulls everything. And my least squares fit would be something that's not accurate necessarily. A larger sample might show that there are actually more of these outliers, and they're not actually outliers. Or a larger sample would put more dots, put more dots where I suspect they should be, better highlighting the presence of an outlier that I can then exclude and recalculate everything to get a much more accurate and representative result. But it's important to be aware that outliers can drastically affect my correlation and regression results. It's a part of the game. It's what happens. I need to be aware of it. Now, the issue of when is something an outlier, when can I exclude it, that is a difficult topic, a little beyond, well, a lot beyond the scope of these videos. And it is also a little bit subjective. But I just wanted to raise your awareness that these outliers can present quite a problem, and I need to sort of be wary of that and watch out for that if that happens in my own study. All right, that is the end for this video. Do look at examples in detail to make sure that you can calculate these numbers, the regression coefficient, correlation coefficient, and so on. I just realized there was one more slide. It's just hiding on the right here. Not a major slide, but something that I want to just mention. And when we get to use software, it's easier to calculate these things that we call multiple regression, where by hand we can cut it off and look at the influence of one variable on my prediction, but I can extend that to more predictor variables. By hand, that is extremely difficult and cumbersome to calculate, so we're not going to do that, but one could with the aid of software. So for example, a person's predicted score, they don't have actual examples here, like sleep and mood, for example. Your mood, which was the Y, your mood rating, can be associated with hours of sleep, how well you slept, number of dreams, for example. And they all have an effect potentially on your ultimate mood rating. So one can do similar things that we did with just the one, but extend that to see how more variables have seemingly an effect on my mood rating in this case. And then if you, by way of software, can calculate these B values and the A value, you can then make a prediction that is arguably more accurate. Your R squared is still going to tell you collectively how much of the variation in Y is accounted for by these variables. And the more variables you can include, of course, the better your prediction is going to be. So just be aware of multiple regression, but by hand, it's a little bit too much, but it's just an extension of what we have talked about so far. Now it is the end of this video. I hope everything is going well, and I will see you in the next one. Until then.